So, continue from where we were. So, we are talking about reverberant field in an enclosure. Now, any point in the reverberant field basically, if I consider in the whole volume of the room enclosure, so it would receive, I am keeping the direct sound out, only the reflected sound, and infinite reflections will reach to any point, like that is what we have seen through this diagram, if you recollect. So, any point in the receiver, if you look at it, receiver, you will get infinite number of reflections coming. So, I can consider any point and there will be infinite number of reflections coming. So, direct path I just eliminate out, I do not consider this, I am only talking of the field, that is because of the reverberant field, that is because of reflection coming from all direction. Since it comes from all direction, we call it diffused, because specular means something like this, specular reflection, right. Diffused means it will go in all directions. For example, if you look at light on a matte surface or a rough, like rough surface, it will spread all in all direction, while if it is a mirror, polished surface, it will go in only one direction. So, that is specular, following laws of reflection and all that. So, since it comes from all directions, it is actually diffused sound, it is diffused, right, coming from all direction and coming randomly, it is not, it is not in one direction. So, random from all directions, so that is diffused field. So, reverberant field is any point in the reverberant field, if I keep the direct field out, then it will receive sound from all directions. And if you look at the whole room, every point will be similar, because every point will receive reflected sound from infinite reflections from all directions. So, you have a diffuse field, in ideal condition it is uniform. So, that is what is written here, consider any point in the reverberant field, sound energy is randomly incident on the point, it is not pinned, it is on the point, it is on the point from all directions, contributed by infinite reflections, and hence in ideal case a diffused and uniform sound field will exist. Diffused because it is coming from all direction, uniform because it will be same throughout, right, and that is what is reverberant field. And you can see that is what, if you remember, this was reverberant field and this constant. So, where reverberant field is dominant, its level is higher, because we said that if I sum up two levels, higher level always dominates, because like you will take the either the intensity, sum of the intensity. So, 60 dB plus 40 dB 60 point something or 61 or whatever it is. So, since in this zone reverberant field will be dominant, it is constant. So, we are assuming uniformly diffused field for reverberant field, right. Now, one can therefore think of constant energy density at every point, because it is uniform. So, constant energy density, that is what we are saying, last class also I was just mentioning, and every point I can treat it as a point source for any other point or any other surface. For any surface, everywhere sound is coming from all direction, and this sound will be travelling in again, it will passing through that point, and from that point it will again go to any location onto the wall. From the reverberant field, sound will also travel to the wall or ceiling or whatever it is, because sound is reflected, sound is reaching there and then it is transmitting. So, it can be treated as a point source. Every small volume, every point in the reverberant field can be treated like a point source, and then we said that it is constant, the energy is uniform, I mean it is uniform, therefore, I can talk in terms of a constant energy density of the reverberant field, right. And what is this energy density? Because if I take unit area on the reverberant field, unit area, let us say if I take some unit area on the reverberant field, like the sound is received from all direction, it is unit area. So, intensity here of the reverberant field, let us say is I. So, I into 1 is the power that is coming in per unit time, and unit time sound travels to the distance c. So, if I talk in terms of energy, energy per unit volume, energy per unit volume, right, energy per unit volume. So, this is coming in t times. So, let me put it something like this is a total energy coming in t time, and t time sound travels through a distance of c by t, it travels through a distance of c by t, c by t velocity of sound is c, velocity of sound is c, right. So, basically through this unit area sound, this is basically the energy density will be c travels in unit time, Ct will be it is what will travel in t time. So, if I divide the volume in which this sound will be contained will be something like this, c into t into 1 again, because area is 1. So, I can write it as I by c or I into 1 by c into 1, whatever it is, because unit time if I take. So, instead of taking t is equals to, I can take unit time. So, c into 1. So, sometime it is denoted by epsilon. Is the idea clear that energy density is I by c, because I is the intensity received on unit surface, and this sound will this sound will be contained in a distance of c into unit volume. Volume will be 1 is the area, if 1 is the unit area, c into 1. So, therefore, energy density is I by c. Last class also we looked into this, I am just repeating the same thing. Our interest actually estimating our interest is to estimate the sound energy incident on any surface. I am assuming from the reverberant field. The reverberant field I can treat it as a point source, right, treat it as a point source every point, and from that how much is the energy incident onto the different walls. Why I am interested? Because some of this energy will come back, some energy will be absorbed by the surface itself. So, I am trying to find out a kind of a reverberant field level, that in order to do that what I need is I should be estimating the sound energy impinging on any small surface or any surface from a point, then integrate for the whole room or the relevant volume, because I am taking one point in the reverberant field, and let us say it is falling on a small surface, right, ds surface, small ds surface. So, this diagram from the diffuse field at let us say in dt time this sound comes. So, I am interested in finding out how much sound is actually incident upon ds surface, any surface, let us say on floor or wherever it is, from a point, and then I can integrate that point appropriately to get from the whole room how much the sound is impinging on small surface ds surface. So, let us say a small volume dV I take in the reverberant field, because I said every small volume I can take it as a point. So, that point corresponds to dV volume and energy density is constant. So, epsilon dV or E dV would be whatever notation I am using is the energy in that small dV volume. So, dV volume let me consider, and that would act as a point source for ds surface, right. In dt time all the points in the hemispherical, how much supposing I consider a surface like this, so this is my ds surface. So, this is my ds surface, this is my ds surface. Now, in time if I am interested in dt time how much sound is falling onto this, I take c into dt distance from here, c is the velocity of sound into dt. So, it will come from all direction because it is diffused field. So, I can consider a hemisphere of radius c dt, and all the energy coming from this volume will be incident upon ds in dt time. Are you getting my point? See the c, basically I am interested in finding out how much energy is impinging or incident upon ds, small ds surface from the reverberant field, which is uniform throughout. I take a small volume, or then I got to integrate it over the volume from where it is coming. The volume that will contribute in dt time, the energy that will come in dt time is simply from a hemisphere of radius c dt, hemisphere of radius c dt, because velocity of sound is c into dt is the distance. So, that will come during dt time. So, that is what I am interested in. Now, I am interested in finding out a small volume. So, take a small volume, right, that is what I have tried to draw I am not very sure whether I have done it very good, but let me draw it slightly bigger. Then it is something like this, this is something like this. What I am trying to do is, this is, there is another arc, there is another arc, there is something like this, something like this, something like this. So, this kind of a small volume I have taken, right, this kind of a small volume I have taken. So, this is, this is I have blue colored, I am trying to fill it in to show it that it is actually a volume, and it will have 3 dimensions. I can treat them as linear. One will be d phi, d theta and dr. So, if I take any volume here, radially outward will be dr, r going from 0 to c dt, right. Finally, for the complete, d phi would be, if I take in azimuth plane. So, d phi is in this plane, this is d phi, some azimuthal plane I can take d phi, and d theta will be in elevation or altitude in the plane, vertical. So, these are all straight line actually. So, this is how I can make, take a small volume I can take like this, right. So, this is what I was trying to do in the last class. Energy density is I by C. I take a small volume there, dV, and I said that dV can be written as r d theta, because this angle is theta, right, and it makes an angle of d theta here. This angle is theta. So, this normal to the surface, and this point is theta, and I am calling this covering it d theta. This part is d theta. So, this height will be r d theta. This height will be r d theta. This is part of the circle. This part of the torus element, if I am talking of. So, this is part of this chord circle, that any whatever is the radius. So, if this distance is small r, this distance is small r. So, I take this volume at a distance r from the ds, small r from the ds, small r from the ds. R would of course vary from 0 to c dt, that is what we have seen. So, r I take at a distance of r, and dr is a radially outward. This is, this one I am calling it d phi, and this vertical one is d theta. So, is this idea all right? So, this is theta, d theta, this is my theta, and this is d theta, and d phi is, one of them is r d theta is r. This is d theta, this is d phi, this is dr. So, three of them would be there. So, r d theta dr, and this one would be r sin theta, because r is this distance, this angle is theta. So, this is r sin theta. So, this is r sin theta. So, r sin theta d phi, because I am taking from the circle volumetric a ring having its sizes defined by dr along this direction. A ring will have three dimensions, isn't it? If I take a small portion from a ring, or if I take a ring, it will have one, a ring will have one direction like this, because I am taking a ring, and it will have I mean, if I take the full ring, then this is one dimension, and full ring if I take. So, it will have a vertical height, and as well as this dimension as well, this dimension as well. So, vertical height and this I am calling as dr, this I am calling as dr, and this vertical one is d theta, r d theta. So, r d theta, and this is small d phi. Phi will vary from 0 to 2 pi, phi will vary from 0 to, this is in azimuthal plane, and r sin theta d phi, that is what I am writing. So, for this small volume, r sin theta d phi, dr is the outward towards the radius, and r d theta is along the elevational plane. So, that is the volume. So, volume of this one is r square sin theta d theta dr d phi. Is that right? Is the volume understood? This is the volume. Now, from this volume, it contributes to the ds surface. So, this is a point source. This is a point source, and it's actually the sound energy is incident onto the ds surface. Now, you see, in order to find out how much sound will be actually coming, it will radiate equally in all direction, because it is diffuse field. A point source radiate equally in all direction. In order to find out how much sound will be reaching on ds surface, I got to find out the solid angle subtended by ds angle, ds surface on the point. Solid angle subtended, from ds. So, this is the solid angle, this is the solid angle, and solid angle is what? Analogy to our regular two-dimensional angle. Angle is defined as arc length divided by radius. So, for a circle it is twice pi, because total arc length is the perimeter of a circle, which is twice pi r divided by r. So, 2 pi, that is a constant actually, that is how, you know. Now, if you extend this idea to 3 dimension, not for surface, for a sphere, 2 dimension is a, you know, is a perimeter you are looking at. Now, you take to the sphere, then it will be 4 pi r square is the surface area divided by r square. So, solid angle subtended at the center of a sphere is 4 pi steradians, right. Now, analogy from planar angle, here we define solid angle as the surface area normal to the direction of the radius. There it was arc length normal to the direction of the radius. So, normal area normal to the direction of the radius divided by radius square. Earlier it was arc length dl, arc length I can say dl divided by r, that is what the d theta, that is what we write. So, here we will talk in terms of d omega, we write it, d omega is equals to dA divided by ds surface area divided by r square, ds divided by r square. Now, let me just write it separately. So, that is what we are saying, ds divided by, so d omega will be equals to ds divided by r square. So, solid angles are defined in this manner, it is the area. Now, that the energy contained in d omega is the total fraction of the energy that will be incident upon ds. Total energy goes out through 4 pi. So, this divided by 4 pi, right, is a fraction of energy that will be incident on ds, but I must take the normal surface. So, ds surface must be taken normal, but you see your surface is like this, ray is something like this. So, I must take the normal surface, that means it will be ds cos theta, ds, because this, you know, this, what was this angle is theta. So, this angle will be, so it will be actually ds cos theta, because I have to take the normal surface. So, ds is this, ds cos theta will be this much. So, d omega will be given by ds cos theta divided by r square, right. And how much will be the total energy going out from this volume? We know the volume was how much? We said r square sin theta d theta d phi dr, right, something like this. Those are volume multiplied by the energy density, if I am calling it epsilon, I mean E by this energy density epsilon, if I am calling it. So, multiplied by energy density, multiplied by energy density, that will be the energy, that will be the energy, and fraction of this energy reaches there. So, that I can actually find out d omega divided by 4 pi r 4 pi, that is what it should come. So, fraction of energy incident on this ds surface I can find out, right, because this is the volume multiplied by epsilon is the total energy contained in this one, which is power of the, I mean which is the source. This divided by dt will give me the power, this is the energy, this divided by dt will give me the power, this divided by dt will give me the power that will come out of this, and w by 4 pi, this divided by 4 pi into d omega will give me the fraction that will be incident upon this ds in dt time. Am I right? Did I make myself clear? What I am saying is this energy density I have found out, multiplied by the small volume dV, that is the energy. This divided by dt, if I am interested in finding out how much energy will come in dt or power. So, power of the source will be W in watts should be this divided by dt, and this divided by 4 pi goes along, 4 pi r square goes along all direction, multiplied by d omega is the fraction which will be received at this one. So, this is what is now, this is what is written, further written. So, this is what is further written, energy density of the reverberant field. So, that is what we are saying. So, epsilon dB d omega by 4 pi, that is the energy that will be received. This divided by d omega is ds cos theta by r square, I have already explained you, and epsilon dB d omega 4 pi. So, that is the fraction of energy that will be received, that divided by dt will be the power that is received. So, you see that if I write epsilon, I have written dB was r square sin theta d r d phi, d omega is ds cos theta divided by 4 pi r square. So, r square gets cancelled. I am left with epsilon sin ds is there anyway, sin theta cos theta d r d phi divided by 4 pi. That is the fraction of energy, fraction of energy that will be received if epsilon dB, fraction of energy that can come in there, right. Now, this divided by delta dt will give you the power that is received. So, if I am interested in intensity, obviously phi varies from 0 to 2 pi, I have already told you, and this we have written like this 4 pi. So, this 2 and 4 will cancel, come something like this, 2 pi, 2 was there, no? So, twice pi by putting this 2 pi d phi, where phi varies, so easily I can write, instead of d phi I am writing 2 phi ds epsilon ds sin theta cos theta d dr, right, divided by 4 pi. So, 4 cancels out and also pi cancels out. So, I am left with epsilon ds sin theta cos theta d dr. That is the fraction of energy coming from a complete ring, because 0 to 2 pi now I have taken. So, it is coming from the full ring, phi is out, rest of the things still remaining. So, total energy received in ds surface in dt time, this will be correspond to the distance travelled by sound in c dt coming from the whole hemisphere. So, when I integrate this with time, right, integrate with time, then I will integrate r will go from 0 to c dt, and theta will go from 0 to pi by 2, because hemisphere I am taking. So, 0 to pi by 2, theta will go from 0 to pi by 2, right, and phi I have already taken going from 0 to 2 pi. So, this is hemisphere I am taking, no, so hemisphere I am taking this angle. So, 0 to pi by 2 it will be automatically covered the other side also, because I have already taken the ring, I have taken this full ring 2 pi. So, if I take 0 to pi by 2, whole of the hemisphere will be covered. So, that is what I am doing. So, energy received in dt time from all direction will be give from the direction is diffuse field is obtained by 0 to ct 0 to pi by 2 epsilon ds by 2, epsilon ds by 2 was already there, epsilon ds by 2 was already there, epsilon ds by 2 I separate it out. So, I get sin theta cos theta d theta, and r goes from c to 0 to 0 to c dt, etc., etc. So, energy received, I only integration that I got to do is here, and this will become simply epsilon ds c dt. Now, sin theta cos theta integration is what? Sin theta cos theta can be written as sin 2 theta by 2, sin 2 theta by 2. So, if you integrate it, you will get minus cos 2 theta by 4, and theta going from 0 to pi by 2. So, I will have actually it will be cos 1 by 4, let me keep it out, there is a minus sign cos 2 theta, this goes from 0 to pi by 2. So, this will be simply 1 by 4 remains, or minus 1 by 4 I can take out, cos 2 pi, cos pi minus cos 0. So, cos pi is how much? Minus 1, and this is again minus 1, cos minus 1. So, minus 2, this minus will go out, this will turn out to be simply half, because this will be 2. So, simply this will turn out to be simply half, am I right? Sin 2 theta by 2, this will become cos 2 theta by 4, this is pi by 2. So, pi by 2 that becomes pi, and minus cos 0. So, minus 2, minus cancels out, I am finally left with half, and finally left with half. So, if I look at this one, I will get this one half, this one c dt. So, energy received will be given as, so theta varies from 0 to pi by 2 as sound comes from hemispherical volume, and after integration, it is shown here again full, and this is equals to half. So, energy density will be given by this, and this will be written as epsilon ds remains, there is a half coming from there. So, it becomes 4, and this is c dt, energy received in dt time. So, what is the intensity there divided by dt? So, intensity at the surface, or energy density, intensity is energy density, or energy come in per unit area per unit time on ds surface is this divided by, right. So, that is what it is. So, energy from the reverberant field will be given by, and you divide by ds to get the intensity. So, you get simply epsilon r by epsilon r c by 4. So, reverberant field intensity on any surface is given by epsilon r, which is from the reverberant field, c by 4, and if I am interested in energy coming in, power received in ds surface, multiplied this by ds, because I is per unit area multiplied by ds. So, anyway, so incident power on surface area of S, now I do not take ds, I take full, let us say larger one, is epsilon r c s by 4, s by 4. So, by doing this, what I have been able to do, I have been able to find out from reverberant field how much will be the energy incident upon surface areas of the wall or ceiling, surface area of the ceiling, roof, walls, ceiling, roof, or whatever you call it, ceiling basically. So, this is the power received on all the surfaces if S is the total surface area of the room. If S is the total internal surface area of the room, then this will be the total power received from the reverberant field into all the internal surface area, where S stands for all the internal surface area, right. Now, whatever power is received, a part of it is absorbed in the wall, and rest all is reflected back. At any time, whatever is a steady condition, for example, is existing, like that I showed earlier, that when you have with time you have decibel level here, and we said the growth and decay of steady field, it will attain some value, remain steady. So, under such condition of steady condition, before I put it off, then it decays. So, this under this steady condition, sound coming in must be equals to sound in gross manner or an average manner. Now, how much is the sound coming in? How much is the sound entering into the reverberant field? No, how much is the sound? It is only talking of reverberant field. So, how much is the sound entering into the reverberant field? The sound after first reflection enters the reverberant field. See, direct field, then after one reflection it just enters the reverberant field and continues to get reflected from anywhere. Some of you might be playing squash, right, but then you take after one reflection, if you just allow it to go for a large number of reflection. So, after first reflection, whatever is the energy comes in, that is what is the sound entering into the reverberant field. How much is going out? Whatever is absorbed in the boundary. So, right. So, this is the amount incident upon the boundary per unit time. Epsilon r c s over 4 is incident upon the boundary in unit time, right. And during this time, the sound that will enter will be given by, if the power of the source which is causing this reverberant field, because you have to have a field which will first have direct field. So, this multiplied by 1 minus alpha bar, where alpha is absorption coefficient, because first reflection, after first reflection, how much will come out? W alpha will be absorbed, direct sound will be absorbed, 1 minus alpha will enter into the reverberant field. That must be equals to the amount of energy lost out of the reverberant field.